Hey everyone, my name is Nathan Johnston, and today I want to go through an example constrained optimization problem with you to sort of illustrate the procedure that you should be going through to solve these types of optimization problems. The problem that we're going to be going through is maximizing the area of a type of window called a Norman window, and the reason I chose this particular problem to go through is because it does a really good job of illustrating each different aspect of these types of problems and what you have to think about to be able to solve them. Okay, so let's just start by reading the problem. It says that a Norman window is a window made up of a semicircle on top of a rectangle such that the diameter of the semicircle is equal to the width of the rectangle that's below it. And then what we're tasked with doing is finding the largest possible area of a Norman window that has perimeter equal to 240 centimeters. Okay, so we're going to break down our approach to solving this problem into a few different steps. And the first step, basically for any constrained optimization problem, and in fact for any math problem, is, well, step one, make sure you understand the problem, okay? What is being asked of you here? And sort of part of that is, when possible, draw a picture, okay? So we're going to draw a picture, in this case, of the window whose area that we're trying to maximize. Okay, so let's just start by drawing a rectangle and drawing a semicircle and plopping the semicircle on top of the rectangle. Now we're told in the question that the diameter of the semicircle is the same as the width of the rectangle, so we know they sort of snugly fit together like this. Now, we don't know exactly what this Norman window looks like yet, right? Because we don't know if we want a very skinny and tall rectangle with a tiny little semicircle on top of it, or do we want like a very short and fat rectangle with a huge semicircle on top of it, or do we want somewhere in the middle? And that's sort of the point, right? Like, there are lots of different possible shapes of Norman windows out there, and what we're trying to do is we're trying to find the one that has, well, okay, we fix the perimeter at 240 centimeters, and we're trying to find the one that has the largest area, okay? But there are lots of them that have 240 centimeters of perimeter. How do we find the best one? That's what we're going to do. Okay, now that we've drawn a picture and we understand what's being asked of us, it's time to go on to step two, which is write down a formula for the thing that you're trying to maximize or minimize. In this particular problem, we're trying to maximize the area of that Norman window, so I want to write down a formula for the area of that Norman window. Now, often this is the tricky part of the constrained optimization problem, coming up with a formula for the thing that you want to maximize or minimize, okay? So we've got to come up with the formula for the area of this Norman window. So let's break it down piece by piece. Okay, this Norman window, it's made up of a rectangle and a semicircle, and, well, we know formulas for the areas of those two shapes, right? A rectangle, its area is just base times height, and a semicircle, well, its area is just 1/2 pi r squared. Okay, so that's fine. Like, the area of the whole thing then is just base times height plus 1/2 pi r squared. But there's a little bit of a problem with just writing it like that, and that is, well, there's just too many variables here, right? We've got base, we've got height, and we've got radius of that semicircle on the top there. Okay, so now at this point, do what you can to reduce the number of variables, or like write the different variables that you've got here in terms of common variables whenever possible. And the thing to notice here is that, like, the base of that rectangle, it's always exactly double the radius of the semicircle. So let's take that into account so that we can reduce the number of variables from 3 down to 2. There doesn't need to be a base and a height and a radius. It suffices just to have a height and a radius. And then note that, hey, that base is just 2 times the radius. Okay, and now we've only got 2 variables left in the thing that we're trying to maximize. Okay, we've got the height and we've got the radius, and we've expressed the area of that Norman window just in terms of those 2 quantities. Okay, if we tried to maximize at this point, there's still a problem. Okay, this formula here for the area, it has 2 variables. It has the height, it has the radius. We can make them both as large as we want. Okay, and as a result, we can make that area as large as we want. Okay, but that's no good. At this point, we've got to take into account the fact that there's a constraint. Okay, and that's what step three is. Okay, step three is look at the question, find a constraint. And in this particular case, the constraint is that the perimeter has to be 240 centimeters. Okay, we can't pick the world's largest Norman window. No, we've got constraints on how big it can be. We've got sort of a relationship between how large the radius can be compared to how large the height is. To actually make use of this constraint, we've got to write down precisely what it tells us in terms of our variables, in terms of the radius of that semicircle and the height of the rectangle. So in this particular case, it tells us that the perimeter of the Norman window is 240 centimeters. That means the distance all the way around it is 240 centimeters. So we've got to write down a formula for what that tells us. So just take this piece by piece. It's very similar to how we came up with our formula for the area of this Norman window, okay? Just, well, we've got a rectangle on the bottom. I need to know, like, how long is the right side and the bottom side and the left side of that rectangle? Well, the right side is h units long. It's the height. The bottom side is 2 times radius, 2r units long. The left side is another h units long. And then all that's left for the perimeter of this Norman window is, well, the perimeter, the circumference of this top half of the semicircle. And that's just equal to pi r, right? If a whole circle has circumference 2 pi r, then the top half has circumference just pi r. Okay, and now we've got our perimeter of this Norman window. It's h plus 2r plus h plus another pi r, and we simplify that a little bit just to 2h plus 2r plus pi r. Okay, now let's make use of our constraint. The way to think about it is it gives you a relationship between your variables, h and r in this case. So what you can do is you can use this constraint, you can rearrange it and solve for one of the variables or the other one. It doesn't matter usually which one you solve for. Here we could solve for h in terms of r, or we could solve for r in terms of h. I'm going to solve for h in terms of r just because, I don't know, that's the one that I picked, so that's what I'm going to do. Okay, so just rearrange, leave all the h's on the left-hand side, move the r's over to the right-hand side, and then we get a formula h equals 120 minus r minus pi times r over 2. Okay, and once we have that, once we have the relationship between the two variables, we can take that relationship and plug it back into the formula that we wanted to maximize or minimize. Remember, we're trying to find maximum area, but we still had two variables in that formula. We had h and we had r. Well, not anymore. Now what we can do is we can replace all of the h's by r's by substituting this entire formula into that area formula, right? We're going to plug what we get from this perimeter constraint into the area formula, and now we're going to have a formula for the area that just depends on the radius, just on r. And the great thing about this is now that area formula, it depends just on one variable. So we can do all of our usual calculus of one variable stuff to optimize this function. In particular, what we can do is, well, find the critical points of this function. So take the derivative, find out where that derivative doesn't exist, and find out where that derivative is equal to 0, okay? And that's going to be our starting point towards actually optimizing this function. So you take the derivative, 240r becomes 240, 2r squared becomes 4r, and 1 half pi r squared becomes pi r, and then just solve for r. Leave all the r's on one side, move everything else to the other side, rearrange and solve. It's just algebra from that point on. Okay, and what you're going to get is, well, r equals 240 divided by 4 plus pi, okay, approximately 33.6 centimeters, and that's our only critical point. Now, depending on the particular optimization problem that you're working with, it may or may not be clear that the critical point you just found actually is the max or min, right? All I know at this point is that it's a critical point. It could be a max, it could be a min, it could be neither, right? It could just be a flat spot in between two increasing sections on a graph. Okay, we want this to be a maximum. Okay, we really need to convince ourselves of that. And I mean, depending on your level of intuition, maybe that's clear, right? If r is really small, then it's a super skinny and tall Norman window, its area is going to be small. And conversely, if r is really big, then it's going to be a super short and fat Norman window. Again, its area is going to be kind of small. It seems like this is probably sort of the sweet spot in the middle where r is sort of intermediate and the area is maximized. Okay, the area will go down regardless of which way I change r, make it bigger or smaller. Okay, but let's really convince ourselves of that. We have a couple different ways that we could classify this critical point, okay? In other words, we have a couple different ways that we could really convince ourselves that it actually is a maximizer. I'm going to do something called the second derivative test. The way that works is you compute the second derivative of your area function, the function that you want to maximize or minimize, and then you check at the critical point, is that second derivative positive or negative, okay? And the reason this is useful, the reason this helps us here is because if the second derivative is positive, remember that means the function's concave up. Its graph looks like a smiley face. And if you've got a critical point in a concave up section of a graph, Oh, it's got to be at the bottom of a valley. It's going to be a minimizer. Whereas if the second derivative is negative, that means it's concave down. It looks like a frowny face. And a critical point in an upside down sort of frowny face region of a graph, it's got to be a maximizer. It's the top of a hill. Okay, so when we compute the second derivative here, we get -4 minus pi. That's negative, right? That's some negative number. It's like -7 point some odd junk. Okay, so it's concave down. That critical point we just found, that's a maximizer. Okay, in particular, it's a local maximizer. Okay, I haven't quite argued what's happening farther away from the critical point, but at least nearby, if I wiggle r just a little bit, the area is going to go down. Okay, but then the really nice thing is there's a theorem that says, okay, if you've got a function of one variable, you're trying to maximize or minimize it on some interval, okay, and you find that, oh, there's only one critical point, like this scenario here. If that critical point is a local min or a local max, it actually has to be a global min or a global max, okay? And that's exactly the situation that we're in here, okay? We're maximizing a function on an interval. We have found exactly there's only one critical point, and it's a local maximizer. It has to be a global maximizer, right? Because if the function were to sort of flip up and go higher elsewhere, okay, further away, there would have to be another critical point in between for it to be able to do that. There's no way for the function to go down on both sides of the critical point and then go up again without encountering another critical point, which we know it doesn't. Okay, so this really is actually a global maximizer as well. Okay, we basically solved everything at this point, but I really recommend whenever you think you're done an optimization problem, go back up and read it again and ask yourself, what is really being asked of me here? And in this particular optimization problem, what was asked of me was not what is the optimal radius, 33.6 centimeters. What was asked of me is what is the maximal area of the Norman window? In other words, what it wants me to do is plug this optimal R, this 33.6, into the area formula and tell me that maximal area, okay? So do that final step, okay? So what we're gonna do is we're gonna take our area formula, 240 times r minus 2r squared minus 1/2 pi r squared, and just plug our optimal r value into that and simplify and plug it into a calculator and get a decimal approximation. And we find that the optimal area, it's about 4,032.7 square centimeters. And then we're done. That's all there is to it. Okay, so that's all I got for you today. Thanks for watching, everyone. I'll plop some links down in the description, like a Desmos graph, where you can play around with this Norman window a little bit geometrically if you like. Other than that, I'll see you all next time.